Welcome back. Obviously, nothing's changed because I don't do edit jobs. We can continue from here with me freestyling, as the term should be referred to, about geometry. Okay, so what is geometry? What is meant by geometry, space, dimensions, coordinates, etc.? What does that mean? How do you define the fundamental existence of geometry? It's very difficult because geometry as a concept has a lot of definitions associated with it, like location, shape, volume, mass, distance, location. It's very difficult to pin down. So what I'm going to do is I'm going to start with the basics. The basics for geometry is space. We live in space. So that's where I'm going to start. Space is basically empty geometry. I know that's me speaking in circles, and I'm sorry, but we're going to have to, there's no other way to do this. So space is empty geometry. What that means is, if you're in your room is space. The distance between any two objects or mass is space. Space is volume. Space is measurements. For instance, the term volume usually refers to like the capacity of a container. Like if you had a one gallon milk jug, the milk in the container is the volume of the container. The volume is associated with the jug itself. Now you can have a cube that's exactly 1 meter by 1 meter by 1 meter. That's length, width, and depth. That gives you a volume. A lot of people don't recognize that, but you can actually say 1 square foot is the volume. I have a volume of 1 square foot. That's important when you're talking about mass and density. The volume, the mass of 1 square foot, of 1 square foot cube of hydrogen is going to have less mass than a 1 square foot of lead because of their density. I'll go into that later. We're going to stay focused on geometry. So, what do we have so far? We have geometry equals space. So we know geometry equals space. And space describes the distance. Space describes the physical shape of objects within geometry or within space or space itself. So my body takes up space. My physical body as an actual measurable object has geometry. It has geometry and it takes up space in geometry, which is the room or the universe itself. The universe itself is truly in geometry. It's geometric. That's why I describe it as geometric, dynamic geometric coordinates. Because to measure geometry, to measure space, to measure an object, you need to define coordinates. Coordinates are little bitty undefined dots that you can subscribe around any object to determine its geometry. If we go to basic geometry right now, and we start with some simple abstract concept as a point, which I don't like using anymore because points are undefined, so I'm going to use the 3D term, a vert, because a vert is defined. A vert is a actual location in three-dimensional space that describes a component of a simple polygon or an object in 3D space. Because objects in 3D space, being geometry, are defined by the program itself. The program recognizes the actual object even if it's not there. You can have an object in 3D space without any verts because the computer keeps track of the information. So it's a very abstract but easily digestible concept to understand. For instance, if I have a simple poly in a computer program called a cube, we know that a cube is a three-dimensional object that has a length, a width, and a depth. And the universe is hard to describe that abstract concept because you need an observer like myself or yourself to describe the actual volume of that cube, where a computer actually keeps track of this information. So that's the point that I'm going to use. We're going to use the computer terminology to establish a position that we can utilize as a reference point for our observations in the physical world, which is special relativity or general relativity. Relativity is the ability to measure and observe information in a very abstract way. So we're going to use the computer as a foundation to observe the universe, which has no foundation, relatively speaking. So what we have is a vert. Vert is a single point. A vert is undefined, but it occupies a length, a width, and a depth in a dimensional coordinate of 3D space. 3D space itself is undefined, but the vert has an actual location in that undefined 3D 3D space in itself is defined. I know. So we have one vert. Let's say this vert is at location 0, 0, 0 on a Cartesian plane. Cartesian plane is an abstract concept and a way of keeping track of and measuring positions in three-dimensional space, because like everything in the universe, space is undefined. It takes human beings to define space. My table has length, width, and depth that is undefined. It has an absolute distance. It's a finite physical shape in the infinite geometry of our universe, but the shape itself is undefined. I can say from one location to the other, next location is 20 miles, or I can say from that location to that location is 10 inches. It takes me to define the actual shape. I'm using those terms incorrectly, yes, because we have given inches and miles exact abstract distances which can be repeatedly measured and repeatedly observed. But the inch as a defined measurement was defined by a mind, body, and spirit similar to myself and given an abstract absolute, but it could have been any abstract absolute. That's why an inch and a centimeter are generally relatively the same distance, even though they have different measurable properties. Measurement, Wikipedia. Anyhow, back to what I was saying. A vert in space is at a location of 0, 0, 0 on a Cartesian plane, which is an abstract way of keeping track of dimensional coordinates, allows you to describe a shape. If you start with a cube or a square, you know that a cube has a length, a width, and a depth. A single vert in 3D space has exactly a length, a width, and a depth, even though it only occupies one dimension. This is why I'm using the computer, because it makes more sense. A single vert in 3D space in the computer program has in fact a length, a width, and a depth which you can plot on a Cartesian plane. The length is x, the width is y, and the depth is z. I'll probably change those as we're speaking, and I apologize in advance, but just remember that 3 dimensions always has a length, a width, and a depth. If I say that the length is x, or the length is y, or the length is z, I should be more accurate, but I probably won't be because I have limitations. But we just want to recognize length, width, and depth for now. So a single vert has a length, a width, and a depth. And you give that length and that width and that depth an actual absolute abstract value, which is usually used on a number. So a single point being x, 0, y, 0, and z, 0 describes the 3 dimensions of that location, of that point, or that vert in 3D space. You can draw another 3D vert with another abstract location of x, 1, y, 1, z, 1. Now you have 2 points. You have a point at location 0 and you have a point at location 1. Those 2 points, you can draw a line, subscribe a line between those 2 points, which is another geometric shape. And in the process, you get a two-dimensional line. If you draw 2 points from that line in 3-dimensional space, you get a cube. You get a plane. You get a square. So you have 1 point. If you draw a point from that line 90 degrees, you get a second point. And that second point gives you a line. And if you draw 2 points, if you draw 1 point from this point in 90 degrees and another point from this point in 90 degrees, you get 2 more points. So far you're at 4 verts, and you have a cube. You have a plane. You have four verts with lines connecting them gives you a plane. No matter what distance or direction these verts are at, you still have, a simple poly that is a square at this point. These 4 verts have to be on the same x coordinate and the same y coordinate. These 2 verts have to be on the same z coordinate. They have to have the same height for them to be a plane. The x coordinate and y coordinate can change relative to the Cartesian plane. They could be as large or small as you want. As long as they're connected and they're on the z-axis at location 0, they are subscribing a 4-sided polygon. If all of the sides are equal, they are subscribing a cube. If 2 sides are equal, if 2 of the sides are equal but are not equal to each other, if side 1 and side 2 are equal, and side 2, if side A and side B are equal, and side B and side D are equal, but side A and B are not equal to C and